All right, what's up, everybody? Digital Asa here, and we're going to be talking about Chapter 2 of Physics 1110, which is all about vectors. This is mostly going to be a math chapter, more so math than physics a little bit, because vectors are going to be really important for us to be able to describe real objects and real space. So this is mostly a mathematical technique that we're going to be able to use to make models, which, as you guys know, is what physics is all about. So when we're making models in physics, we really want to make a coordinate system. And the way we're usually going to do this is by using the classic Cartesian coordinate system. This is named after Rene Descartes, the mathematician. The philosopher whose famous quote is, "I think, therefore I am." We are going to be using his coordinate system. And that is the coordinate system that you're most familiar with in math. So it's like a plus axis like this. This is the x-axis. We call this the y-axis. If you add a third dimension in the third direction, we're going to add that axis kind of going into the page here. We would call that the z-axis. But for now in physics, we're just going to talk about the x and the y. So we have the x-axis and the y-axis, and usually we're going to name this direction the positive x-axis, this direction the positive y-axis, this direction the negative x-axis, and this direction the negative y-axis. That's negative x, that's negative y. However, you can pick where 0 is. You can pick which directions plus and minus are as well. You could, just as easily, if you wanted to, call this direction negative y and this direction positive y. All of your math will come out the same, so long as you keep it consistent. So as long as you're calling everything going in this direction positive and everything going in this direction negative, you can switch them however you want. But the classic Cartesian setup is like this. That's positive x to the right, positive y up, negative x to the left, negative y down. But again, you decide where your 0 point is, your origin, as you'd call it in the coordinate system, and you can make plus or minus whatever direction you want. Okay, so that is the Cartesian coordinate system. This is usually what we're going to be using to represent our model. Okay, so what is a vector? A vector is a measurement that has both a magnitude and a direction. If you guys remember the movie Despicable Me, there's a character in that movie named Vector, whose villain name is Vector, and he names himself because he commits crimes with direction and magnitude. Oh yeah, that's his quote. So direction and magnitude, what does that mean? It means it's a measurement that has an amount and an associated direction. And we're going to represent this with an arrow. The length of that arrow is going to be the magnitude. The way that arrow points is going to be the direction. So basically, the long and short of it is that any measurement that has a direction is a vector. Any measurement that does not have a direction with it is just called a scalar. Scalars only have magnitude, no direction. Oh, geez, it's a bad line. There we go. So scalars are just numbers. Directions are arrows that have both an amount and a direction. The direction is determined by the way the arrow is pointing, usually represented by an angle, and the magnitude is represented by the length of the arrow. So the example I gave earlier was if I'm moving 75 miles per hour north, north, the 75 miles per hour is my magnitude, the north is my direction. Okay, so there's a way we can tell, an easy way we can tell whether a measurement is a vector or a scalar, and that's basically just, does it make sense for this measurement to have a direction associated with it? So let's go ahead and draw two examples of this. The first example, Asa tripped and fell down the 22-degree slope like an idiot. He rolled for a few seconds, eventually reaching a velocity of 6 meters per second. So this is a example of text that you might see in one of our physics problems that we solve later. So let's say we wanted to draw a model of me rolling down a 22-degree slope. So what we're going to do is we're going to draw a slope like this. That angle is 22 degrees here. I am falling down it. Here's me. And I've got a velocity of 6 meters per second. So this is how I would draw a representation of that situation. Likewise, let's look at another one of these. So Cole launched the ball with a mighty velocity of 14 meters per second, making his throw an angle of 37 degrees at the ground. Okay, so we have Cole, who is a quarterback from my class a couple years ago. He's got a football, and he's going to throw it with a velocity of 14 meters per second. And the angle is going to be 37 degrees with the ground. So basically, this angle will be 37 degrees from the horizontal plane. So I would represent these two situations by drawing this vector. So this vector's got a direction of 22 degrees down the slope, down diagonally, and a magnitude of 6 meters per second. This vector has a direction of 37 degrees and a magnitude of 14 meters per second. So notice also, I drew this second arrow as being longer than this first one. The length of the arrow usually represents the magnitude of your vector. So a long arrow is a high number for your magnitude. A short arrow is a lower number. Okay, so let's do our first Dora the Explorer problem. Scalars versus vectors. This is a pretty easy one, but I want you guys to try to pause the video and figure out whether the following measurements are scalars or vectors. So pause the video, try to figure out whether all of these measurements are scalars or vectors. You got position, velocity, mass, acceleration, energy, and time. Okay, welcome back. So we want to figure out whether these are vectors or scalars. The easiest way to do that is actually quite simple. I call it the direction test. And the direction test is very simple. All you have to do is basically ask yourself, does this make sense if I put a direction after my measurement? If the answer is yes, it's a vector. If the answer is no, it's got to be a scalar. Okay, so position, for instance. Well, I would describe my position as like in meters, right? It's like, oh, I'm 35 meters away from the door. Does that make sense to put a direction on it? Okay, I'm 35 meters north of my cat. I'm 25 meters to the left of the soda machine. Yes, that does make sense with the direction, so it's going to be a vector. Velocity. Velocity is like a speed, so we'd measure that in meters per second or in miles per hour. So I'm going 45 miles per hour north. Yeah, that makes sense. So that's a vector. Mass. Well, this object weighs 75 pounds. 75 pounds southeast. That does not make any sense. So that's got to be a scalar. Okay, what about acceleration? Well, when you're accelerating, are you accelerating in a direction? Slam on the gas pedal in my car speeds up forwards, it doesn't speed up backwards, that's directional. Acceleration is going to be a vector. What about energy? Well, if I think about like the direction my car is moving, right? Whether it's moving north or south, if it's moving 200 miles an hour, it's got the same amount of energy. If I were to slam into a wall, it would have the same amount of energy in that collision, regardless of whether I was going up, down, left, right, north, south. So energy is going to be a scalar. And then time. Well, okay, it's been 30 seconds. 30 seconds north, 30 seconds south. Doesn't really make sense. Time only ever really moves forward. So time is also going to be a scalar measurement. So basically the idea behind the direction test is you can easily tell if something's a vector versus a scalar if adding a direction to your measurement makes any sense, right? So pretty easy to tell which is which. And again, vectors have an associated direction, scalars don't. Basically, the long and short of it is anything that you care about the direction of, any measurement that you could possibly care about the direction of is a vector. Anything else is a scalar.